Welcome back to the last part of polynomial functions and their graphs. We're going to look at the intermediate value theorem for polynomials now. If f is a polynomial function and f of a and f of b have opposite signs, then there exists at least one value c between a and b such that f of c equals 0. Now let's just unpack this statement. If I look at f of a, the output for the value a, where a in this case is 2, clearly gives an output of -3. So at f of a, we get -3. Now if I look at f of b, it's somewhere right about here at, I don't know, 1.5 maybe. So f of b is positive. So it means that between the value a, which is 2, and b, which is 3 in this particular graph, we have a value in the middle, an intermediate value, that is crossing the x-axis. So that value c is right where the function as a whole equals 0. So in result, we can accept that for 2 consecutive zeros, the graph of the function is either above the x-axis or below the x-axis. We'll decide this by test points. We can also decide this by using factors. If c is a 0 of p, then x minus c is a factor of p of x. Suppose x minus c appears m times in the factorization of p. Then we say that c is a 0 of multiplicity m. This is the formal definition. If m is odd, the graph crosses the x-axis at c. If m is even, the graph touches the x-axis and c and does not cross it. Now let's take a look at example 4. We need to graph the following polynomials by finding their zeros, their multiplicities, and their end behavior. For the first example, we have p of x equals the quantity 2x squared minus 18 times the quantity x minus 3 cubed times the quantity x plus 5 to the 5th. Let's go ahead and factor all of these, and I'm just going to list them out. It's going to be a lot of factors. How do I know that? Practice. So we've got 2x squared minus 18. If I factor out a 2, I will have an x squared minus 9. And I happen to know that x squared minus 9 factors to x plus 3 times x minus 3. So I've taken care of my first interesting binomial. Now, x minus 3 to the third means I have an x minus 3 times an x minus 3 times an x minus 3. Oh boy. And then I have 5 x plus 5s. X plus 5. I'm going somewhere with this. Trust me. Okay, so let's highlight these. The 2x squared minus 18 is this first set of factors. This x minus 3 to the third is x minus 3, x minus 3, x minus 3, all multiplied together. And this last x plus 5 to the 5th is these last 5 binomials, x plus 5, all multiplied to each other. Now, it might seem a little excessive to do this, and in fact it is kind of a little excessive, but I want to show you why I'm doing this. Notice that there are more x minus 3s than just the ones in the x minus 3 raised to the third. There's actually an additional x minus 3 here. So now that we know all our factors and we've listed them all out, we can then rewrite this with the multiplicities assigned. So we have 2 times x plus 3 times x minus 3 raised to the 1, 2, 3, 4. Because I have 4 x minus 3 binomials. And I still have the same number of x plus 5 binomials, so it will stay x plus 5 raised to the 5th. If I were to look at the leading coefficient for this polynomial p of x, all I have to do is multiply the coefficient or constant 2 to x times 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 x. How many of those were there? Well, we have a leading coefficient of 2 times x to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ta-da! Okay, that's our leading coefficient. We now can determine the end behavior. Our end behavior is a positive even degree. So now I can sketch the graph of this. I can determine what my end behavior is, and I'll sketch that first. I know it's leaving from the top left and the top right. I can identify my roots because I know that I will have a root at -3, at +3, and at -5. Now I need to determine the multiplicity so that I have the correct behavior. The multiplicity on the binomial x plus 3 is 1. That corresponds to the behavior at the root -3. So this one, since it's degree 1, it will cross straight through. Now let's look at 5. So my multiplicity on x plus 5 is a cross and flatten out at the root. So we'll say flatten and cross, or cross and flatten. Hopefully you know what that means now that we've discussed this quite in detail. And then the last one would be at x minus 3 to the 4th power. So my multiplicity is 4. This means it's a kind of smushed parabola. So no cross. It does not cross if it's an even multiplicity. And it's higher than 2. So the higher the power, the more flat it gets at that point. So it's a fairly flat one. So we'll call it a flat bounce. And now I'm just going to connect my dots. This is my favorite part. So I need at -5 to cross and be flat at the cross. So there's my crossover from the top of the x-axis to the bottom of it. I know I need to cross straight through -3. So I have to come back up and go through -3. I cannot cross at +3, but I do have to have a flat bounce. So I have to come back down. So kind of like that. And then it heads off to positive infinity. And we can adjust the end behavior. But the end behavior clearly was where we wanted it to be. Our roots directed us through kind of a maze, and we got to the end behavior we needed. We started on the correct side of the graph, the top side, and we left from the top side, so everything was good. Hopefully this makes sense. I'm not going to go into that much detail every time I sketch one of these, but for the first time it's always good to see where I'm getting the numbers. So in f of x we have 3x minus 1, x plus 6 raised to the 3rd, and 2x plus 3. Our roots will be at x equals 1/3, x equals -6, and x equals -3/2. Our multiplicity is 1 on the first factor, 3 on the second factor, and 1 on the third factor. We need to determine our end behavior. So let's multiply these together. I have a 3x, I have an x to the third, and I have a 2x. That will give me a 6x to the fifth. That means it's a positive odd degree, which means I will have end behavior on the bottom left and the top right. Now I literally just have to wiggle through the roots. We'll say this is -3/2. Further left is -6. Clearly this is not totally to scale. And then I'll say on the right of 0 is 1/3. Now I just remember that the rules say at -6, I have to flatten and cross over. At -3/2, I have to go straight through. And at 1/3, I have to go straight through again. Now, if I look at my end behavior, it does indeed match the shape that I had originally anticipated. So I didn't do anything wrong when I was crossing the roots. Let's take a look at C. We have q of x equals -x to the third minus x squared plus 6x. First, let's factor out a negative x. This will give me an x squared minus x minus 6. Now I'll check to see if I can factor this x squared minus x minus 6 further. An x and an x, a -3 and a +2. My negative x stays out front. I already know that my leading coefficient is negative and odd. So I'll just say it's a negative odd degree polynomial. Now I will put the roots in place. I have a root at x equals 3, a root at x equals -2, and a root at x equals 0. My end behavior is negative and odd, which means I will start on the top left quadrant and I will end on the bottom right quadrant. Now I just wiggle through the roots. At -2, my multiplicity is 1, so I go straight through. At 0, my multiplicity is 1, so I go straight through. And at 3, my multiplicity is 1, so I go straight through. And hey, look at that! My graph is behaving as it should at the ends. It went through all my roots. I'm good to go. Now let's look at the last example we have here. I think D might be just a little bit more complicated just because there's so many things to factor. Don't freak out though. We have an x squared minus 2x plus 1. We don't have to worry about this one too much, other than that negative sign out front. And the x cubed plus 3x squared and the plus x plus 3, that's a factor by grouping. So let's start on the left. This first one's going to factor to an x and an x, a -1 and a -1. This one we just have to keep track of that negative sign because it will change the sign of the overall polynomial. With this factor by grouping, we can factor out an x squared, and we'll be left with an x plus 3, and then plus 1 times x plus 3. All right, so our final factors, if we take these out, we'll have an x squared plus 1, an x plus 3, a negative x plus 3, and an x minus 1 quantity squared. Now this x squared plus 1, that is an imaginary root. It has a plus or minus root -1, so plus or minus I. and we can't graph that on a normal graph, but we still have to keep track of the degree, okay? So don't forget the degree, but we can't graph it on our real x and y axis. So we'll have an x squared, a minus x, so now we're at a negative x cubed, times x squared again, so now we're at a negative x to the fifth, times x plus 3, so negative x to the sixth. This is our leading term, so it is a negative even degree. Now if I graph it, I will have roots at 1, at 3, at negative 3, and that pretty much does it. Remember, we can't use the x squared plus 1. Now we have to look at multiplicities. At 1, I have to bounce. At 3, I go straight through. And at negative 3, I go straight through. Discussing end behavior, if it's an even degree negative, that means my end behavior will be in the bottom left and bottom right quadrants. And now I just wiggle through the roots. Cross straight through at negative 3. Bounce at 1. Go straight through at 3. And ta-da! My end behavior matches. So remember, local max and local min. Those local extrema is the set of all local max and min points. Note that the graph of a polynomial p of x of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 down to the last two terms a sub 1 x plus a sub 0 of degree n has at most n minus 1 local extrema. It's important to point out that it says at most. It could have less than that. So in our case, we had this x squared plus 1 that had imaginary roots. They're still real roots. You just can't see them on our standard two-dimensional graph. Note that the graph has 1, 2, 3 local extrema. If we had had this x squared plus 1, it would have given us 2 more, which would have given us 5 local extrema, which would have been 1 less than the degree of this polynomial. It's just kind of a weird and interesting pattern that just happens when we're looking at polynomials. This should give you enough information to now be able to complete all your homework in this section, and I hope that you take some time to just practice graphing polynomials. It would also be really cool if you could take some time to graph these same polynomials in Desmos and see how, even though the scale might be a little off in how I sketched these, they still have the same end behavior, the same behavior at the roots, and the same positive and negative regions based on the multiplicities.